The Socrative app coming in. Let's go ahead and check the first one here. It says use the answers from the Socrative app quiz to correct or complete your molecular geometry table in your handout. So if you don't have your handout out, let's get it out here. First of all, in a molecule of NH3, the nitrogen is surrounded by blank electron groups, which includes blank bonding groups and blank lone pairs. Looks like we did very well here. 4 electron groups, 3 bonding groups, and 1 lone pair. Any questions on this one? Actually, we'll look at the first 3. Next one, electron geometry of NH3 is the total 4 groups. It's going to be tetrahedral. Tetrahedral. Next up, the molecular geometry of NH3 is, correct answer there, trigonal pyramidal. Now, to do this one, I have some structures that are, I suppose we can look at okay, so if we look at the 4 pairs around the central atom, remember that the electron pair geometry is one that is tetrahedral. We get the electron pair geometry, the electron group geometry, by removing all of the atoms from there and looking at the arrangement of the electron pairs in 3-dimensional space. 3 of those are used up as bonding groups, like this. We still have the 1 lone pair. We get the trigonal pyramidal because as it sits here, it has a triangular base and forms the shape of a pyramid with the nitrogen atom up above the plane. So to get these now, I would not anticipate one would have probably memorized it by today. You should, however, have this memorized by your exam time. And I did post, this is something that appears on page 436 in your text. So that's one way you can figure it out, page 436. Then there's some additional information on page 439. And then I think we said it was 458, which is kind of where we're headed here today. 458. Let's see, yeah, page 458. So 436, 439, and 458 is all put together in this one table. So if you look at the electron pair arrangement here in this first group, you would count the bonding groups and the lone pairs. And so in this case here, we have 3 bonding groups and 1 lone pair, makes it the trigonal pyramidal structure. And NH3 happens to be shown here as one of those examples. Any questions on the NH3? All right, then going on to the next ones, which was with reference to SF4. Sulfur is surrounded by 5 electron groups, of which 4 are bonding groups, and we have 1 lone pair. If you had drawn it out, you would have drawn it out initially something like this right here. You would have had an extra lone pair that you would have placed around the sulfur at the very end. The electron geometry, which is the next question, is the trigonal bipyramidal. That's because we have a total of 5 pairs around the central atom. And that would be this one right here, and the 5 pairs around the central atom. And then if we want to get the molecular geometry on this one is seesaw. Now, we get this name because of this. We put this on here, this is like a teeter-totter or seesaw. Now, when we wind up arriving at this structure, this is one that when we talked about the Vesper model on Tuesday, we had said that what we'd like to do is we'd like to minimize the repulsions in the molecule. And if we look at this, once again, how many lone pairs are on this model? Just 1. So one of the options here is to place this on this plane that goes around here. Another option would be to move this, and would be to place the lone pair in this position, kind of along this axis here. So when we look at it then, we go back and remind ourselves which electrons are held most closely to the central atom? Lone pairs. So since lone pairs are held more closely to the central atom, what we'd like to do is we'd like to minimize the repulsions. So in this case here, we look at where this lone pair is located. What we see is that if we want to minimize repulsions, this lone pair here is at a 90-degree angle to 1, 2, 3 other electron groups. However, if we move it into, move this one, there we go. If we move it into this position right here, we see the lone pair would be at a 90-degree angle to only 2 other groups. So which position is it that would minimize the repulsions? This one here? Yeah, it would be this one here. And it would not be this one here because there'd be more repulsions in this one because it's at a 90-degree angle to 3 other pairs of electrons. So consequently then, we wind up with this shape here. We're on the trigonal bipyramidal electron group arrangement with a single lone pair. Again, it's on that plane that goes around. We call it seesaw because, again, if you look at just the atoms in the molecule, it acts like a teeter-totter or seesaw. So any questions on the structure? All right, and I am aware that I have a very big zit on my head, okay? And I know that when I've sat in your seat before, it's very easy to get fixated on that. So do your best not to, because I am very conscious of it. And just as I was walking down here, one of my colleagues said, "What did you do to your head?" And it's just like, it's a zit, all right? So anyways, it did make me laugh because even before I came in here, I was saying, I know I got this big zit on my head, and she called me out on the walk down here. So anyhow. Final exam in here is next Tuesday at 11:50. It is S245. There's the review guide down in the library. We talked about checking that out if you want to take a look at it. It is a full year review guide. So when you do look at it, just do keep in mind that we are looking for 1 semester only, whatever we cover here in the first half. Only non-programmable calculators are allowed. I do have about 12 of them here that I can loan out, and let's just do a quick check again here. How many is going to need one just to see if that number's changed at all? 2, 3, 4, 5, 6, 7, 8. So we're still in there. As long as everybody who didn't raise their hand comes with their non-programmable calculator, we will be in good shape then on Tuesday. When we come in here on Tuesday, we'll just have you sit down. We are going to arrange you alphabetically like we have done in the past, unless you have your special seating request. We haven't gained or lost anybody since the last exam, so we'll be the same layout as we had for the 4th exam. My office hours next week look like this. And let's see. Anybody happen to go to the final exam review session yesterday? Okay. We have another one today. It appears at 3 o'clock down in the Academic Support Center if you wish to attend. We do need our table of electronegativities out today, so let's get that out. Any questions about the final? Let's see, what do we have next? All right, table of electronegativities. If you wrote on it like we did before, I've saved my notes from before, which remind us what the electronegativity stands for. The electronegativity stands for a relative measure of attraction in atom places on shared electrons. Now, in the absence of actual values, we should remember the general trends in electronegativity, and that is as we go across from left to right, the values will increase. As we go down within the group, the values will decrease. So again, I can't tell you what is coming up on the standardized final, but as long as you know the trends, you're in good shape. If you need specific values, they will be provided for you. And then here are the 2 items filled in, how one might draw them in if they were to draw out the structures on the table that we didn't quite complete here the other day. So any questions on these? Go ahead, Don.
I noticed that for low pairs in N3, there's like no line. Is that normal? Do you not have any kind of like line or line there?
Where?
The 2 dots.
Oh, for the 2 dots? Yeah, you can show them. And it actually brings up a good point, because who came, was it you that came to my office yesterday? Who was asking about the drawing? Sierra, who's not here. Okay, so if you are doing your master in chemistry, it's asking you to draw out the structures. And when you're drawing out your structures, I don't know how that moved. Okay, well anyhow, when you're drawing out your structures, the structures on master in chemistry, I believe when you're showing up the geometry, you do not include the dots on there. So I think that he was working on it really hard, and then found out that, we're only asking for just what the structure is and not to fill in the actual dots themselves. Yeah, yeah. Yeah, if you run in that situation, just send me an email that you did, because okay. Yeah, just send me an email if you ran into that situation. I'll give you some points if I look at your structure or whatever you tried submitting and got it right there at the beginning. Okay. So next up then, here's how we're going to wrap up. There's a few loose ends that we have yet for the course. And those loose ends will be, there we go. Need to put this in. We're going to talk about polarity here today. And to talk about polarity, something is wrong, because all my pens are not showing up. So I don't know why that is. We are sorry. OneNote is cleaning up from the last time it was open. Please wait. There we go. Okay. So polar bond and nonpolar bond. If electrons are shared equally, which one would it belong to? Equal sharing. This one right down here. This one is where electrons are shared equally. Just think of the names. If it's nonpolar, that doesn't, if something's polarized, it means one is favored over the other. So if it's a polar bond, we said the electrons are not shared equally. Now, your author also gives this another name. It refers to nonpolar bonds as pure covalent bonds. This is more of your author thing. So to determine the polarity of a bond, we go back and look at the electronegativities. And if we look at the table of electronegativities, we can tell how equally electrons are shared based on their electronegativity. So if the electronegativity values are the same, that means they have an equal attraction for shared electrons. If the electronegativity values are different, that means they do not have the same attraction for shared electrons. The larger the value, the greater its attraction for shared electrons. So based on that, we'd say that fluorine here has the greatest attraction for shared electrons. And the one that would have the least then would be francium down here. This would have the least or lowest attraction for shared electrons. Now your text goes a little bit further, and I don't think we need to know this, but just in case it shows up on your final, there's some criteria where it will say, well, if the difference is in electronegativities is 0 to 0.4, we say that this is a nonpolar bond. If the difference is 0.4 up to 2.0, then we call it a polar bond. And if it's 2.0 and above, then we say that the bond is ionic. But again, I don't think you really need to know this distinction. Usually, just make it very clear. To me, it's if it's zero, it's nonpolar. If they're different, then it's polar. And if it's metal to nonmetal, then it is ionic. And that would be the best way to wind up looking at it. Okay? So, going from here then, most students don't have any problems with the polarity of bonds. Turns out that the most trouble comes from the polarity of molecules. And so we look at what we say is a polar molecule and a non-polar molecule. And to determine the polarity of molecules, we need to look at the three-dimensional structure of the molecule itself. And I could give you definitions of these, but I think these are probably best done by example. So what we're going to do is we're going to look at some structures. We're going to start with NCl3. We're going to draw out the structure of these molecules. We'll have NCl3, have Cl2, and HCl to begin. And let's quickly draw out the Lewis structures now that shows the correct three-dimensional shape. And so if you had gone through everything with the NCl3, you would find that there's going to be 4 pairs around the central atom, or 4 electron groups. And since there's only 3 atoms, that means that we kind of want to draw it something like this. Show that that nitrogen sits up above the plane. So I'll draw it something like this, and then we'll have the chlorine, which we can very easily draw like this here. And then we have HCl, which we can write out like this. Now to determine molecular polarity, we go back to our table of electronegativities. And we'll look them up here for, first of all, nitrogen and chlorine. We look at them for nitrogen chlorine. Nitrogen has a value of how much? 3.0. Chlorine is at 3.0 as well. I'm going to write that down here to remind us what these values are. Now, because these values for both nitrogen and chlorine are the same, that means that if we look at each bond individually, and by each bond individually, we look at this bond, consider it separately, this bond, consider it separately, and this bond here, consider it separately. In each case, we compare the values of the electronegativity. It's not like we take nitrogen then divide it up by 3 because it's forming 3 different bonds. We compare 3.0 to 3.0 here, 3.0 to 3.0 here, and 3.0 to 3.0 here. So in all of these cases, what types of bonds are going to be present? Nonpolar, exactly. So we'd come back here and say that all bonds are nonpolar. So this one's nonpolar, this one's nonpolar, this one's nonpolar. Once again, because the electronegativity values in all cases are the same. When the electronegativity is the same as it is in all of these cases, what we say is that the molecule itself is nonpolar. So this is an example of a nonpolar molecule. Now the next one, we wouldn't even need to look up the electronegativities. We have 2 like atoms bonded together. We have 2 like atoms bonded together. In all cases, the molecule is going to be nonpolar. Because of course the electronegativities are the same, which means that the bond here is nonpolar. If all the bonds in the molecule are nonpolar, then the molecule itself is a nonpolar molecule as well. So again, this is going to be a nonpolar molecule. The bond itself here is going to be a nonpolar bond. If we go on to HCl, we once again look up those electronegativities. We see hydrogen at 2.1, chlorine sits at 3.0. So again, hydrogen at 2.1, chlorine sits at 3.0. We now have a difference in electronegativities. And because we do have a difference in electronegativities, this bond in here is going to be polar bond. Okay, so the bond itself is going to be a polar bond. Again, because the difference here is 0.9. Now, to determine whether the molecule is polar or nonpolar, we can look at it a couple different ways. One of the ways that's done is like this. First of all, we remember what the electronegativities mean. It means that the larger the electronegativity, the greater the attraction for shared electrons. And electrons now have what type of charge? This can be a negative charge. So because we look at this and say now which atom in this molecule has a greater attraction for those shared electrons? It's going to be chlorine, because chlorine has the largest electronegativity. We would then label the chlorine here as having a partial negative charge. The hydrogen over here gets labeled as a partial positive charge. Now, I don't know how far any of you have made it in mathematics or in calculus. Have any of you talked about partial derivatives in there? Okay, so you've talked somewhat about partial derivatives. You know that this letter here represents the Greek letter delta. When we write it like this, it's a lowercase delta. That delta represents partial amounts. And so now maybe calculus books have changed, but in the past they would write it as a partial amount on there like that. And so these represent partial amounts. This here then represents partial positive. This represents a partial negative charge. Again, they're partial charges because the electrons are still shared. It's just that they're not shared equally. And what this is telling us is that those shared electrons are spending more time with the chlorine than they're spending with the hydrogen. And because electrons have a negative charge, that means that this atom then, even though it hasn't gained those electrons, but because those electrons which are negatively charged are spending more time with the chlorine, this gets labeled as a partial negative. Yes, Alex? Yes, they can. And how would they have a stronger polarity? Exactly. So in this case here, now, unfortunately, we're not going to get into great detail on that. That's one of the very first topics of Chem 2 that you look at. We talk about the example of water being very polar, because if you look at water, you have hydrogen sitting at 2.1 and oxygen at 3.5. So the difference there becomes 1.4, and that's a very large difference in electronegativities. And when you have very large difference in electronegativities and hydrogen's involved, we have something called hydrogen bonding that takes place. The hydrogen bond is not a chemical bond, but it's attraction between molecules in which hydrogen is bonded to either nitrogen, oxygen, or fluorine. So yeah, exactly. You kind of think of it kind of like magnets if you want to. The greater the differences in electronegativity, basically the stronger the attractions they're going to be, and they're going to be more like magnets and want to attract each other when they do so. So very good. Anybody else? Okay, here's the other way it's you look at them, and which way shows up on the final, I can't tell you, because there's two different ways that polarity is represented. The other way it's represented is by drawing, oh, didn't tell you what a molecule is polar. Here's how we tell what a molecule is polar. If we can take a plane, and by a plane we're talking about a flat surface. If we can take a plane and separate it, so all the partial positive atoms are on one side of the molecule, all the partial negative atoms are on the other side of the molecule, then we say that the molecule is polar. So again, if you can take a plane and separate and get all the partial positive atoms on one side, the partial negative atoms on the other side of a molecule, then the molecule itself is said to be a polar molecule. Now it's easy when there's only two atoms like this. Now another way that it's sometimes done is drawing vectors. And in drawing vectors, what we do is we draw an arrow along each bond that always points to the more electronegative atom. And we kind of put a cross in it over here. The cross is by the one that is more partially positive. And we draw them and point them towards the more electronegative atom. If we do it like this, if we have vectors that in effect do not cancel each other out, and well, there's nothing to cancel out here. We just have one vector that we draw in. If they don't cancel each other out, and that is there's a net direction like there is here, and that direction is pointing here towards me, then we say that the molecule itself is polar. So there's a couple different ways we can go about determining or showing polarity of a molecule. Let's look at another one. Let's look at carbon dioxide, CO2. Now I've actually have built those models here using a virtual molecular model kit. In fact, if you want to build molecules and play around with them like this, you go to just do a quick Google search on virtual molecular model kit. And if you look up virtual molecular model kit, you can build your own models and show what they look like in 3 dimensions. But this is a molecule of CO2. And if we come back here and draw out a structure of CO2, that structure of CO2 would look like this. In fact, I think this is one of them we probably put in our table. Molecular geometries on Tuesday. So now if we look up the electronegativities on this one, we'd see that carbon has an electronegativity of 2.5, oxygen here at 3.5. So we write them down here. Carbon sits at 2.5, oxygen sits at 3.5. Well, now we go back and label the atoms as partial positive and partial negative. Remember, we consider along one bond at a time. So in this case here, we would label carbon and oxygen. What's one gets labeled as partial negative? Oxygen will. And then, of course, if we look at this bond, the one that gets labeled partial negative would be oxygen as well. So we come back here once again, labeled partial negative, partial negative. Carbon in the center is one that is partially positive. Now our criteria is that we should be able to take a plane, and we might try putting plane all sorts of different ways here, but we want to try to get a plane that we can get all the partial positives on one side, the partial negatives on the other. Is there any way we can get all the partial positives on one side, the partial negatives on the other? There isn't. So if we can't separate them one side to the other, then we say that the molecule itself is a non-polar molecule. Even though in this molecule, what types of bonds are present? Well, they're double bonds, but are they polar or non-polar? These are polar. The bonds themselves are polar. The bonds themselves are polar, but the molecule itself is one that is a non-polar molecule. Now, if you want to look at it in terms of vectors, remember what we're going to do is we're going to draw along each bond a vector and always have it pointed out towards the more electronegative atom. So if we went along this bond, we'd point out towards the oxygen. And like the little cross there could kind of be towards the one that is more electropositive. So we're pointing it out towards the more electronegative atom. And likewise in this case, pointing out towards the more electronegative atom. Now if you do vector addition, and I don't remember where you cover vectors in your math, I haven't had these before, kind of think of them like a tug of war. What happens if they're pulling away from each other with equal strength? In vectors, what happens to them? They cancel each other out, right? They cancel each other out, it's basically left in the middle. So there's no one direction winning, And so since there's no one direction winning, that is another support for the fact that this is a non-polar molecule. Okay, any questions on this one? Okay, then if we look at this molecule, we're going to look now at NH3. And NH3, this is one that we drew out when we first came in here today. This is one where the nitrogen sits up above the plane. And then if we drew this out and show the hydrogens in here, we would wind up with something that looks like this. And of course, we have the lone pair up above. If we look up the electronegativities on this one, we'd see that the electronegativity of nitrogen sits at 3.0, hydrogen sits at 2.1. So again, nitrogen at 3.0, hydrogen at 2.1. So now if we go ahead and try labeling these and see what happens, which element gets labeled partially negative? Partially negative. Nitrogen does, because it's the one with the largest electronegativity. We see that this one here is partial negative. The hydrogen is labeled partially positive. So now the question is, can we take a plane and separate, get all the partial positives on one side, partial negatives on the other? Can we do that with this one? Yeah, we can, because all we need to do is go right through here. We have all the partial positives, which here are in contact with the table. They are on a different plane than the nitrogen, which sits up above the plane. So because they are on different planes, and you can take a plane and separate, get the partial positives on one side, partial negatives on the other, then the molecule itself is one that is a a polar molecule. So again, we say that this molecule is polar. The bonds in here are what type? Right, all bonds here are polar bonds. Now, if we did this with vectors, we would draw in some arrows along each one of the vectors pointing towards the more electronegative atom. So if we do it with vectors, we would draw up along this one, point it towards the nitrogen, draw up this way towards the nitrogen, up this way towards the nitrogen. So again, think of all of these here. They're all going to be pointed up towards the nitrogen in here. What's going to happen to the vectors? They're going to wind up pointing in a net direction that is upward. Okay. Now they're all going to cancel out in this plane right here, in the XY plane, but they will not cancel out in the Z plane. So there is going to be a net upward direction in here, which tells us that the molecule itself is a polar molecule. So that's part of the reason why we spend time with three-dimensional geometry, is simply because of the fact that we need to do that to look at the polarity of the molecules. And you might say, well, why the heck should we care about the polarity of molecules? What does that do for us? Well, we talked already about how it can cause attractions between molecules. So we're going to look at a couple different molecules here. And the molecules I'm going to have you look at will be water and hexane. Water, of course, is H2O. Hexane is C6H14. So now what I'd like for you to do is draw out a Lewis diagram for each one of these molecules. Draw out a Lewis diagram for each one of these molecules. Right, a Lewis diagram for each molecule. Remembering that water has what type of shape? Bent, exactly. No, you don't have to make hexane very hard. I'll tell you right now that hexane has a backbone of carbon atoms. Well, it's reminding me of some vocabulary that I probably should bring up. We go back to polarity for a moment. So hexane looks something like this. And before we get too far, again, vocabulary that you should know uses the terms dipole moment. Dipole moment. And this is a physics term. And it's kind of related to like a moment of inertia, though there's no inertia involved here. But it basically refers to whether there is a even distribution of electrons around the atom. If we have an atom that has a dipole moment, this is the same as saying it is a polar molecule. So if it has a dipole moment, then it is the same as saying it is a polar molecule. And if it has a zero dipole moment, that's the same as saying it is a non-polar molecule. And we get that term also from the fact that if we analyze the word dipole means something that would have two poles. And a polar molecule is something that has two poles. It's going to have a partial positive and a partial negative pole. So you'll sometimes hear referred to as a dipole or having a dipole moment if it is a polar molecule. So we come back to this one here now, and I have a couple of liquids. And I think we did this on day one in here. Does this look at all familiar? No? Okay. So if we haven't seen it before, we're going to see it today. Did we see this day one? Yeah? Okay. So now what I'm going to do here is I'm going to take a balloon. And this one's going to work well today because it's really dry outside. And of course, when we demonstrate this in August, when we started this course, it doesn't work so well. But if you can't see, why don't you get over here and take a peek. And let's see if we can tell which one of these would be hexane and which one of these would be water. So let's look carefully. Make sure you can see the stream of liquid. I'm going to bring the balloon up next to this. You'll see that nothing's happening to this one. And I'll go ahead and open up this burette. Now, can you see what's happening to the water? Yeah, gave it away. So which one is water? This last one. And why? How can we tell that this one's water? All right, it's a polar molecule. So when we started this class, I said by the end of the semester we'd be able to describe what's happening and why. And the reason why the stream of liquid is being bent towards the balloon is because water is comprised of polar molecules. And so what I've done here by rubbing the balloon in my hair is I built up a static charge. I built up some extra electrons. So when they get in the presence of this balloon, which has a static charge, those molecules of water will all orient themselves so that the partial positives are attracted towards the negative electrons that are built up here on the balloon. And so one of the ways you can demonstrate this, and you can do this at home if you don't have balloons at home, You can always demonstrate this with a comb, but just get a thin stream of liquid up there. And you can see that by bringing the balloon up to the stream of liquid, you can get the liquid to be attracted to the balloon. And it works great this time of year because of the low amount of water molecules that are in the air. If we did this back like we did in August, you might remember that there wasn't a whole lot of traction because all the water molecules in the air are picking up the electrons off the balloon itself. So, all right, any questions on that? All right, so now that we've shown that they behave differently, then we might go back to why should we care? What relevance does this have? Well, there's a general solubility rule that says this. It says likes dissolve likes. Likes dissolve likes. And what this means is that substances comprised of polar molecules tend to dissolve other substances comprised of polar molecules. And substances comprised of nonpolar molecules tend to dissolve other substances comprised of nonpolar molecules. Now, notice we're talking about the polarity of the molecules, not the polarity of the bonds. So when we talk about likes dissolve likes, we're talking about the polarity of the molecules. Nonpolar dissolves nonpolar, polar dissolves polar. And if something is really polar, like water is, it can also dissolve ionic compounds. So what I can do here with this is I can go ahead and take some of these liquids. This one here is the hexane. And I can add it to this one here, which is the water. And of course, the water being more dense, where is it going to go? The bottom, right? And I'll add a little more to this one. And I'm going to go ahead and get another test tube set up with these. Put in the hexane here. And then we'll put some water in it as well. Now, if the hexane, how can we look at the hexane and tell that hexane is nonpolar without even calculating electronegativities? Right, there's no way we can split this with the plane here and get all the hydrogens on one side, the carbons on the other. So even without looking up electronegativities, you should be able to look at this one and tell that this is a nonpolar molecule. So now that I have the two of these in here, I can go ahead and take the two liquids and shake them up. If I quit shaking, what's going to happen to them? It should wind up separating back into the two layers, okay? Now, something kind of cool about this is, now, let's say that you want to try to separate things. You can sometimes separate things based on their polarity. So if I now introduce a couple of different substances, one of them being not copper 2, this is cobalt 2 chloride, and this one here is iodine, which is I2. And we don't need to look this one up. I2 is going to be what type of molecule? Nonpolar. Cobalt 2 chloride is going to be, won't be polar, this is going to be an ionic compound. The ionic compound should dissolve in water. The nonpolar iodine should dissolve in the hexane. So we can put that really quick to the test here to see if that's true. And where's my, if I had a, here it is. We'll go ahead and put some of these into each one. I'll open them up. We're going to put the cobalt 2 chloride in the one that's to your left. And then we'll put the iodine into the one that's going to be on your right. I'll take a few flakes out of here. Put that in. And then we'll cover these up. And we'll shake them up a bit. And then we'll watch what happens when we do that. Now again, I like to pick these out because they have some color to them. And if I quit shaking them and take a look at them, what we should see is that the iodine went into the hexane, which is the nonpolar, the top one. The cobalt-2 chloride went into the water, which is the bottom one. So now if you're trying to get into the separation of things, you can separate things based on their properties of polarity. Okay, any questions? So one of the ways that this works is back in the day, back in my day when I was driving cars around as a teenager or whatever, we had to put heat in our cars in the winter and heat it. Now I know they still sell it, but if they sell it to you, don't buy it because it's a scam now. If you go and buy heat, heat is methanol. And if you buy something like isoheat, that's isopropyl alcohol. There's something that has a mixed polarity. But back in the day, what would happen is that in the middle of winter, we can get water in the gas line. And the gas line with that water in it will wind up freezing. And then the gas could not get from the gas tank over to the engine, to the carburetor, right? So what you do then is you would dump in some heat, which is really either methanol, or if it's isoheat, it would be isopropyl alcohol. And isopropyl alcohols tend to have a mixed polarity. They're both polar and nonpolar. That would mix everything together, and then it would prevent the gas line from freezing, and then it would go all the way through. Why do we not need it in Minnesota today? Well, we have better gas systems, but there's another reason in Minnesota why we don't have to. Our gasoline today contains ethanol already. That's by law. So the ethanol, which has a mixed polarity, then will already be mixing the gasoline and the water together and pull it all the way through. And detergents work the same way. Detergents have a mixed polarity, or soaps. They are both polar and nonpolar, and they can wind up mixing together oil and water. If you try to wash grease off your hands, you can't do it. So you add in a detergent which has a mixed polarity. All right, we got to wrap things up here. So we need to go through what's called hybridization. Hybridization. And hybridization deals with the orbitals. We refer to it as orbital hybridization. Orbital hybridization. Now, to look at orbital hybridization, we're going to start, first of all, by looking at water, which is, of course, H2O. And let's look at the Lewis diagram for water, which again looks like this. And let's look around this water molecule and count up the total number of electron pairs, electron groups. How many groups are there around the central atom here? There's 4 groups, all right? And we said that if there's 4 groups, we have a shape that we call tetrahedral. So let's look at and figure out how this happens. To do that, we are going to look at, first of all, an oxygen atom, which is the central atom that's in here. And we're going to start by writing out its electron configuration, and then we're going to write out its orbital diagram. So we'll start with the electron configuration for oxygen. And we need a periodic table here. So if we want to figure out the electron configuration for oxygen, this sits in the P1, P2, P3 sits in the P4 column. And we write out its configuration as 1s2, 2s2, 2p4. And then we could write out the orbital diagram for oxygen. Write out an orbital diagram for oxygen. So if we write out the orbital diagram for oxygen, it would look like this. We have the 1s sublevel. We've got the 2s sublevel. And we've got the 2p sublevel. Now putting in the electrons, what happens when we get to the p? Put one in each box and then we double them up. Now if you remember anything about the p orbitals here have three distinct orientations. And the three distinct orientations are: one lies along the x-axis, one orbital lies along the y-axis, and one lies along the z-axis. And in terms of angles to each other, how do these angles compare to each other in these models? They're at 90 degrees to each other, right? So these are 90 degrees to each other, these are 90 degrees to each other, and these are 90 degrees to each other. But if we go back to a water molecule, the bond angle that we find in here is how much? Well, it's not 109.5, but it's 105 degrees. As long as you know it's less than 109.5, remember we're going to be okay. And so if we're talking about putting on hydrogens and sharing these electrons, we would expect that if it's using these p orbitals that the angle ought to be 90 degrees, and it isn't. So the way that we account for the fact that it's not 90 degrees and never is to produce what are called hybrid orbitals. And to make the hybrid orbitals, we then count to see how many groups of electrons there are around the central atom. And again, in this case, there's how many? There's 4. So what we're going to do then is we are going to hybridize 4 orbitals all together. And we would state it like this. We are going to hybridize to yield 4 orbitals of equivalent energy. Hybridize to yield 4 orbitals of equivalent energy. And if we hybridize them together, the net result winds up looking something like this. We still have our 1s subshell, just like we've drawn before. But now we have 4 orbitals of equivalent energy, which we'll go ahead and label like this: 1, 2, 3, 4. And if they are of equivalent energy and we place the electrons in, they follow the same rules as before. We place 1 electron into each orbital before we begin doubling up. And so what we're left with is something like this. We still have the 2 orbitals, but now because these are all of equivalent energy, they occupy a space in 3 dimensions, which places them as far apart from each other as possible. And in the case we talked about on Tuesday, that angle winds up being 109.5 degrees. And what happens then is hydrogen comes in with its 2 valence electrons. So the electrons that come from hydrogen are the ones here that we're showing in red. And so 2 of these pairs, one being the lone pairs, because these are the ones that come from the oxygen itself. These 2 here are the bonding pairs of electrons. So these here are the lone pairs. These 2 here are the bonding pairs. The orbitals themselves are called sp3 hybrid orbitals. sp3 hybrid orbitals. And we get the name sp3 hybrid orbitals because in order to make them, we look at what we use to make them. And that is how many p orbitals were used? 3. And how many s's? 1. So we call them sp3 hybrid orbitals because they're made of 1 s and 3 different p's. And again, the hybrid orbitals are 3 orbitals of equivalent energy. Now, if you've had genetics at all and talk about hybrids take on some properties of both ones from which they're derived. So a shape of a hybrid orbital winds up looking something like this. As you remember that the s orbitals have a spherical shape and the p orbitals have this dumbbell shape. And in the end, then they wind up forming orbitals that have 2 lobes, but one lobe is much larger than the other. And again, then they wind up orienting themselves in 3-dimensional space that places them as far apart from each other as possible. In the case of 4 hybrid orbitals, that shape winds up being a tetrahedral shape. In the case of water, 2 of those get used up as bonding pairs, 2 of them out here remain as lone pairs. Then we get the bent molecule. So any questions on this one here? Any questions on this one? Okay, then we look at SF4 as an example. This is the one that when we came in today. We want to talk about how we exceed the octet rule. So if we look at SF4, and again, we're going to go back and draw the structure we had when we first came in today. We had the sulfur bonded to the fluorine. Actually, 4 fluorines. We've drawn it something like this. And of course, the lone pair. Again, we're just redrawing what we drew coming into class and starting today. Showing the 5 pairs of electrons around the sulfur. So now to explain the hybridization in SF4, what we do is this. We're going to go back and look at the central atom. And so we're going to kind of follow through the same sequence that we did back here. First thing we did is we drew out the electron configuration of the central atom by itself, and then drew out its orbital diagram. So we'll do that with the sulfur. We're going to look at the electron configuration for sulfur. And when we look at the electron configuration for sulfur, which is right here, we can go back to the previous noble gas, which is neon, and put the neon in square brackets. Then we write what comes after that, which will be these 2 here, which takes us up through 3s2, and these here, which would give us 3p4. 3s2, 3p4. So from here, once we write out the electron configuration for that element that's in the center, the next thing we do is we write out the orbital diagram for that central atom. So we write out the orbital diagram of a sulfur atom. And when we write out the orbital diagram of a sulfur atom, we start with a neon, and then it looks like we have 3s2 and the 3p4. And just like before, when we write in those electrons, we place 1 electron into each orbital within the subshell before we begin doubling up. Now, if we stopped at this point right here, it would look like we only have the ability to add in 2 atoms. And we see that that's not the case. We actually added in a total of 4 atoms And if we count even more thoroughly, how many pairs of electrons, how many electron groups are on the central atom? There's a total of 5. So what that means is we need 5 orbitals of equivalent energy. Right here, we only have 4 orbitals to work with. So what happens now is that the third energy level has available to it a 3D subshell. At this point, the 3D orbitals are empty. But since we need 5 orbitals all together to make the 5 electron groups, what we do now is this. We say we are going to hybridize. So we're following kind of the same sequence. We are now going to hybridize to yield not 4 orbitals of equivalent energy, but 5 orbitals of equivalent energy. So again, we say, and I'll put this in red here, we're going to hybridize 5 orbitals, hybridize to yield 5 orbitals of equivalent energy. When we hybridize to yield 5 orbitals of equivalent energy, we then start with the neon, and now we have these 5 orbitals that we want to show of equivalent energy. We would show 1, 2, 3, 4, 5. Now the label that we'd give to these, remember we called these back here sp3 hybrid orbitals. And we call them sp3 because we used one s and 3 different p's. What would we call this one here? S, P, 3, D. So it'd be an sp3, sp3d hybrid orbitals. Now we don't write superscripts of 1. If we did put superscripts of 1, it would be S1, P3, D1, because we used one S and one D. So these are your hybrid orbitals. And then we place these electrons in there. So how many valence electrons does the sulfur have? It has 1, 2, 3, 4, 5, 6. So again, 1, 2, 3, 4, 5, 6. So I place them in here, 1 electron into each orbital before we begin doubling up. So now we double that one up right here. And that means we have 4 unpaired electrons. And those 4 then can be used to bond to the fluorine. So we can then show the ones that come in from the fluorine right here, 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 here. And these here then are the ones that come from the fluorine that we're representing with the down arrow. And so what this shows us is that we have a total of 4 bonding pairs, which is what we're showing in the SF4 molecule. And we have a total of 1 lone pair, which is what this model up here is showing us, the 1 lone pair on the sulfur. And so this is a way then that we can exceed the octet rule. We exceed the octet rule by using the empty d orbitals that begin in the 3rd energy level. Now if we go back to our summary table, and the summary table, this is kind of my grand review of everything. This is what I call a summary in a page. If we go back and kind of look at this, here's how we kind of put these together. If we have 2 electron groups around the central atom, we have what are called sp orbitals, and that's it. And that should make sense because if we have 2, that means we're going to hybridize a total of 2 orbitals. If we have trigonal planar or 3 groups around the central atom, that means we need to hybridize a total of 3 orbitals. So we use one s and we use 2 p's. If we go on to having 4 around the central atom, we have sp3 hybrid orbitals. If we go to 5 groups around the central atom, we have sp3d hybrid orbitals. And what happens if we go on to 6 around the central atom? sp3d2, exactly. So we use one s, we use 3 p's, and we use 2 d's in order to make the sp3d2 hybrid orbitals. And I know you want this to be over, so do I. But one more thing that I know that you're going to probably see on your final. And that is this. I'm trying to get it done here, folks. They are the distinction between what we call sigma bonds and pi bonds. Sigma bonds and pi bonds. And here's what these things are. Sigma bonds. These here represent the first bond between 2 atoms. And what we say is that the overlap is the orbital overlap is along the axis between 2 atoms. There's going to be one more point that we're going to make on here. Pi bonds. These here represent the second and third bonds between 2 atoms. And on these here, we say that the orbital overlap is on opposite sides of the axis between 2 atoms. And it's a very important distinction that we need to show. I'm going to go back to these models. I'm going to show sigma bonds first. When we talk about sigma bonds, we say that the overlap is along the axis between 2 atoms. So if you can imagine these 2 red pieces coming together and overlapping with each other, if the overlap is along the axis, that means that one of the things we can do is we can go ahead and spin them around, and the overlap is going to remain intact. Okay, it will stay intact. That's what it would be in a sigma bond, is if the overlap is along the axis, then the overlap is going to stay intact. If we go to pi bonds occur when the overlap is on sides opposite of each other along the axis. So if they're on sides opposite of each other, what happens if I go ahead and twist these? If I twist them, do we have any overlap anymore that occurs? No. If there's no overlap that occurs when I twist or turn these, then what that means is that we wind up breaking those bonds. Well, since the bonds aren't going to break, what happens then is that when the overlap is on sides opposite of each other, that basically holds them into these rigid positions. They cannot rotate. Whereas when the overlap is along the axis between them, this allows for rotation to occur. Now, if I were to show a quick example of that, here's a case where we have single bonds. We have single bonds. What happens in this molecule is that they are free to rotate. Free to rotate because the overlap is along the axis. So what that means is that if I draw this with the 2 chlorines on the same side, that's the same as drawing it with the 2 chlorines on opposite sides, because these are in continual motion. Atoms within molecules are in continual motion, just like atoms or molecules themselves are in continuous motion. And this is always happening in these molecules. But if now you think of this axis between the 2 atoms here, and the overlap is on opposite sides. If I try to rotate, again, what happens? I can't spin it around. Okay, so again, the overlap is on either side. So now, when I look at these, if I have these two molecules right here, notice both of these have 2 carbons, 2 hydrogens, and 2 chlorines. But are these molecules the same as each other? No, and why are they not the same? Yeah, if you look at this one here, the chlorines are on opposite sides, and this one here, the chlorines are on same sides. This holds them into fixed positions, and they can't rotate. And that gives the molecules some inflexibility. Whereas in this one here, it's continually in motion. Sometimes they are on the same side, sometimes they are on opposite sides, and again, it's in continual motion. So if we were going to put down our last bullet points on here, we can say that this one here, the sigma bonds, this allows for rotation. Along the axis between the 2 atoms. And the pi bonds, this here prevents rotation along the axis between 2 atoms. If you are taking the second semester of this course, this will be one of the first things you'll be starting with in here. And you're going to learn that the difference between these two is the difference between what we call cis and trans isomers. This is a trans isomer, this is a cis isomer. It has implications when you look at things like fats. And maybe you've heard of trans fats before. Trans fats are ones that have rigid bonds in there that lock in molecules on sides opposite of each other. So that's where it is. Any questions that you have here on this material or going into the final exam? Any questions? All right, I'm going to finish today with a little story. All right. Was the night before finals, the lab was quite still, not a Bunsen was burning, so the air had a chill. The test tubes were placed in the racks with great care, in hopes Professor Chemistry soon would be there. The students were sleeping all snug in their bed, while visions of formulas danced in their heads. When outside their lab there arose such a clatter, I sprang from my stool to see what was the matter. When outside the lab there arose such a clatter, yes, when what should I say? Whoops, I messed that up. When what should appear in the sky, dare I say? I saw 8 tiny ions pulling a sleigh, and holding the bonds tied to each one of them was the little old driver, the great Professor King. More rapid than catalyst, the charges they came, and he whistled and he shouted, and he called them by name. Now nitrate, now phosphate, now iron and oxide, on copper and chromate, on silver and chloride. To the top of the school, to the top of the wall, now dash away all. As I drew in my head and was turning around, down the fume hood he came with a bound. A tray full of beakers he clutched to his heart, and under his arm was the periodic chart. His eyes through his goggles I just couldn't see, for his hands were all yellow from HNO3. He spoke not a word, he had no time to kill. He filled all the test tubes without even a spill. Then placing them back on the tables with care, he dashed to the fume hood and rose through the air. He sprang to his sleigh, gave his ions a whistle, and away they all flew like the down of a thistle. But I heard him exclaim as he left the scene, "Happy finals to all. May you live out your dream." All right, that's it. It's been a pleasure having you this semester, folks.